formula that's down at the bottom, okay? So 5 cosine of t, 5 sine of t, and square root of 11t. Alright, so you guys see our little scrolly line that we made. Alright, in section 12.5, we learned about how to find lines in space. And we talked about how lines actually need to be explained more specifically than planes, because instead of being anywhere on a big plane, you're just specifically walking a tight line. And so the way that we were representing lines, it would look something like this: 5 plus 2t, negative 3 minus t, 8 plus 4t would be an example. The 5, negative 3, 8 could be thought of as a starting point. And the 2 and the negative 1 and the 4 are telling me about slopes in the respective directions, but it's the slope related to the parameter t that you're plugging in. So this is representing dx dt. This is representing dy dt. This is representing dz dt. The slope in the x and the y and the z directions. Okay, but that's how you trace a line in space. A plane is not going to have separate little equations. It's just going to be one equation with x, y, and z in it. If it's missing a variable, then it stretches out in that direction. Okay, but you don't have to be restricted to lines. We could make any kind of curve in space. And how do you do that? Well, you do it like I just did. I have a separate formula that explains how to get x, a separate formula that explains how to get y, and a formula that explains how to get z. And you represent that sort of like a vector. So I could write it the way I did there. If you wanted to use your IJK notation, you could use that. The variable is t. You might want to think of it like time. So I'm plugging in, negative time if you like to count down, or, often if you're trying to picture, some substance to the t, you can think of it like time. That's probably why t gets used. But it's just a variable that's helping you trace the curve, and you're tracing the curve relative to what you're plugging in here. Okay, so this combination would give you that spiral. So that's the first main topic of chapter 13, is just the idea of, how do I draw curves in space? How would I do that? Well, you would do it by explaining separately how to get x, how to get y, how to get z. Does that make sense? Okay, we already did it because we were doing that when we were finding equations of lines. Once you have a curve in space, you can start to study all kinds of things about it. You could find the length of it between a starting and ending point. You could find tangent lines to the curve. So that's kind of one main topic that we'll talk about, is finding tangent lines to the tangents to the curve. So when you were back in count 1 and you were trying to find a tangent line to a curve, the slope of the tangent line was given by what?
Derivative.
The derivative. So the tangent vector to a curve is given by the derivative of your space curve. By the way, there's lots of different names that this goes by. I noticed the applet is calling them space curves. You also hear them called parametric curves. You also hear them called vector value functions. Okay, I think Maple used to call them vector value functions. The software we used to use. So they're just different names that refer to the same idea. They're called space curves a lot because it's a curve out in space. They're called vector value functions because I'm defining the points on it by a vector. It's called parametric because parametric is the idea of describing different components by separate formulas. And you find the derivative of this the way you think you should. You separately take the derivative of the x and from the y and the z. So this is minus 5 sine of t. This is positive 5 cosine of t. And then this would be the square root of 11. Okay, so in general, that explains how to get tangent vectors to that curve. So if I were interested in a specific point, why don't we just find it at 1, okay? So if I, here, I'm gonna, okay, notice the z doesn't change, it stays square root of 11. So I can graph the vector 5, wait, it's negative 5, right? 5 sine of 1, 5 cosine of 1. I'm just typing in and the square root of 11. And we're starting from 0, 0, 0. Oh no, actually, I don't want to start at 0, 0, 0 if I want to really see this vector. I want to start it at the point, so I want to start it at 5 cosine of 1, 5 sine of 1, and then because I plugged 1 in for t, the z is also square root of 11.